Hi everyone. So in this video we're going to show that Tikhonov regularization converges in the small noise limit. So I'm going to call m beta, and I'm going to find g beta as this normal equation that we had from the previous video, getting its inverse. And then I'm going to split the data as true data and noise, where the true data actually has, it can be expressed this way through true model parameter. And then the error is just going to be the difference between those two. So we want to show that this term gets small as beta and the noise go to zero with each other. So I can rewrite m beta as g beta d, and then the data is g beta times, so it's d true, which is fm true, plus the noise minus m true. And so we get g beta f minus the identity times m true plus g beta eta. So I'm going to call this purple term E beta noise, and this peach term I went below the E beta bias, because we're biasing our solution by introducing this beta, right? If beta is equal to 0, this term is actually, it ends up being 0. So let's deal with the bias term first. Okay. So g beta f is f star f minus plus beta I inverse f star f with tildes everywhere. And then we use, we had that f is unitarily diagonalizable, so we can essentially just put u and u star and then just multiply the corresponding diagonal parts. Where now we have this lambda squared term. Okay, so that tells us that E beta bias is the sum dun m true un times, okay, so then what are these diagonal elements? So we're inverting this term and we're not inverting that term, so it ends up being lambda n squared on top, and then we divide lambda n squared plus beta. And then we subtract the identity, right? So keep this in peach, sorry. So g beta f minus the identity is g beta f minus u star, which is u times the same thing minus the identity times u star. So we have minus 1 here is the main idea there. So it's the same manipulation times un. Okay, now in the limit that beta goes to 0 of E beta bias, this is 0. because I get lambda n squared over lambda n squared minus 1. That's 0. And then if you if lambda n were 0, this wouldn't pop up in the inner sum at all. So so we don't have to worry about 0 eigenvalues. Or, well, actually, no, yeah. So if we had 0 eigenvalues, the operator is not invertible anyway. So we're assuming it's invertible, so that it has all non-zero eigenvalues. So then let's move on to the noise component. So that component's pretty easy to deal with. It's pretty clear that it goes to 0 as the regularization parameter goes to 0. So E beta noise is G beta eta. And so this is equal to U lambda squared plus beta I inverse lambda U star eta, which is the sum. So how am I getting that again? Well, G beta, it's the same thing we had in the previous video and right there. So again, I'm using a unitary basis, so it's like just multiplying their diagonal components. That gives me a lambda squared plus a beta, invert it, and then multiply by another lambda. So then again, we get this. Now we just have a lambda n on top, right? So then as I take beta to 0, I get 1 over lambda n, which does not go to 0, right? Times un. Okay, so call it f beta of x is x over x squared plus beta. So let's maximize and minimize this so that we have a bound. So this is going to be x squared plus beta minus 2x squared over x squared plus beta all squared. And we're going to set that to 0. That implies beta is that x is minimized or maximized at x is plus or minus beta. And so that tells us that the absolute value of f beta is less than or equal to, because this will be symmetric, the square root of beta over beta plus the square root of beta, beta plus beta, 1 over 2 radical beta is what that ends up being. And so that tells us, so if I take the norm of both sides, it's an orthonormal basis, so it's just the sum of its components. So it is squared. Sum of its components squared. Let's call it f beta of lambda n squared is less than or equal to 1 over 4 beta times the norm of eta squared. So it's all two norms. So we want this error to go to 0 as the noise level goes to 0, right? Because if the noise level is a certain limit, we can't expect to recover anything. But as the noise level goes to 0, we're fine. So if we take beta to be the order, eta to the p, that tells us that E beta noise is less than or equal to order eta to the 1 minus p over 2. So we require p less than 2 for that term to go to 0. And all that we required here was that beta goes to 0. In other words, that beta is order n to the p with, if we want to use polynomials here. So p has to be greater than 0 for that to happen. And so in the end, we want this condition. 0 less than p less than 2. And so this gives us a theoretical, we want this property to be preserved, and if that's the case, then we get convergence. And then in the next video, we'll cover how do we choose beta. How to choose beta, and how we choose beta is based on this estimate regarding fitting it within the noise. And that'll be through two main ways of doing this is Morozov's discrepancy and L-curve analysis. So that's what we'll cover in the next video, and I hope to see you guys there. Thank you for watching.